In the previous videos, we developed some intuition for interferometry, and to keep it simple, while we developed intuition, we used simple one-dimensional examples. In this video, I'm going to do the formal derivation of the relationship between the sky intensity or the image of the sky and the visibilities. That's the Fourier transform relationship, which we spoke about in the previous video. This is the sort of derivation you would find in standard textbooks of interferometry. So you can call this the formal derivation of the basic equations of interferometry. What we are interested in is I of S, and that is just the brightness of the sky in direction S, where you can think of S as a unit vector, which is pointing at the direction you're interested in. Now, I is usually called specific intensity, and it has units of ergs per second per hertz per square centimeter per steradian in Gaussian units. So you can think of I as the energy that is coming in from some direction on the sky, and that energy you're measuring per unit area on the Earth, per unit time, and per unit bandwidth, and per unit solid angle of that pixel on the sky. Okay, so that's the most basic quantity you can measure to understand how bright sources are in the sky. Now, we have to somehow relate this specific intensity to what we measure on the ground, which is just the electric field. And for that, we use Poynting's theorem. You can find this relationship derived in any classical textbook on Maxwell's equations and electrodynamics. So the specific intensity is related to the square of the electric field. And this equation just is one of the terms in Poynting's theorem. Now, because the astronomical sources are so far away, their radiation reaches to us as plane waves, like we said in the first video. So I can write this electric field, which I'm going to measure on the ground. So that's the electric field vector as coming from a direction S as a function of R, which is the position on the ground where you're measuring this. Now that's going to be related to, of course, the square root of the specific intensity. And again, I'm taking a time harmonic case. So I'm taking a monochromatic electromagnetic wave, which is coming in. So that's going to vary with time as exponential of j omega t. And of course, I need to now write the extra geometric path delay, which we've been talking about in the last two lectures. And if you remember, there was a trigonometric term there, sine of theta, where theta was the zenith angle. Now, all of that can be written in a vector format as r dot s by c. So that's the extra geometric path delay, which you get to position r on the ground. Okay, so that's the electric field, which is on the ground. And that is what we will be measuring if there was one source on the sky. Now, there is radiation coming from all directions. So the electric field due to all directions is just going to be the integral overall solid angles on the sky. And that's written in the last equation here. So this is just the integration over solid angles of this equation. So that's the electric field I would measure at a position R on the ground. Now, we're going to define the visibility, which is the two-point complex correlation function of the electric field. Let us define the visibility as given here, where E of R1 and E conjugate of R2, that is basically the two-point correlation function. And because all the signals we get from sources are stochastic, which is to say they are noise-like, they are not deterministic signals. That's why I've put here an ensemble average. So I need to understand this as the statistically expected value of this correlation. Okay, so that's what these angular brackets denote. Now, you don't have to worry too much about these kind of normalizations, C by 4 pi. I've formally included them here, so the units make sense. In practice, this doesn't matter so much because in the end, what we actually measure by recording the electric field in a computer and then correlating it, that is not going to be in real units anyways. It's going to be in units of whatever the sampler is doing in the electronics. And eventually we convert everything to actual real units by calibrating against a known astronomical source. So it's a source of known brightness. Okay, but formally I've included these so the dimensions make sense. So anyway, so now if I write the electric field due to the entire sky, I'm going to now get a double integral because I'm multiplying the electric field at position R1 with R2. So I need to now integrate twice over solid angles, and I get this double integral, and that's the electric field. And if you notice this term here, this is very similar to the beam forming term, which we spoke about. Okay. So now there is another simplification that is possible for astronomical signals, and that comes from the fact that one location on the sky is emitting independently of another location on the sky, which is to say that the electric field fluctuations because of one source are not correlated to the electric field fluctuations on the ground because of another source, just because these two sources are stochastic sources that they don't know about each other. So their electric field fluctuations are not correlated, which means that this double integral is greatly simplified simply because this expected value goes to 0 when S1 is not equal to S2. Okay, only when S1 is equal to S2 will there be a correlated component in this expected value over here. So because I of S1 and I of S2 are statistically uncorrelated, their fluctuations are statistically uncorrelated. When you take the expected value, you can simplify this simply as a delta function. So if only when S1 is equal to S2 will there be any contribution to this statistical correlation, simply because different sources on the sky are independent of each other. They don't know about each other. So one of the integrals, of course, drops out only when you integrate over this delta function. One of these integrals will drop out, and then we get an equation for the visibility between locations R1 and R2. That's the R1 and R2 are the two locations which form the baseline. So you get an integral over the whole sky of the sky intensity multiplied by this geometric term here. And you can already see that this basically looks like a Fourier transform relationship. So we are almost there. We just have to do a little more algebra to put it in a form which is directly useful for us. So again, some notation to make things simpler. If you remember from previous video, we said that because these sources are very far away from us, where you build the telescope on the Earth doesn't matter. You should measure the same specific intensity at a given direction on the sky, which means that all of this equation should only depend on the baseline length, which is the relative displacement between R1 and R2. It shouldn't depend on the exact locations of R1 and R2. So let's call B the baseline vector, which is R1 minus R2. And then we get visibility on a baseline vector B is just equal to the beam solid angle integral of the sky intensity distribution with this complex phasor. Okay, and now this is basically is a Fourier transform relationship in 3 dimensions. And that's basic. That is the basic equation we are going to work with. Now, of course, when we build telescopes on the Earth, we can do one more simplification here. Let's suppose that all of our telescopes are on a flat plane on the Earth. Then some more simplification is possible. We can reduce a lot of the 3-dimensional nature of this equation into 2 dimensions. So we can go ahead and do that. So let's define a Cartesian basis where the direction vector S, I can write it as the x component and the y component. So remember, S is a unit vector. It points to the direction of the source. So the x component of that is typically in the literature called L. The y component is called M. And in a later video, I'll actually define where exactly we should choose the x and y axis and the z axis to lie to make our life simpler. But for now, let's assume that there is a Cartesian coordinate system and not worry too much about which way the axes are exactly oriented. Okay, so we have L and M, and that's all you need to figure out a position in the sky, because S is a unit vector. So M is just going to be equal to the value that makes the length of the vector S unity. So that's the Z component in this Cartesian basis. Okay, so I'm going to also now write the same for the baseline. So let's define the baseline length projected on the x-axis of this Cartesian system in units of the wavelength as u, and similarly the baseline projected on the y-axis in units of wavelength as v. So this is the standard notation u and v, which are used for the plane in which the visibilities are defined. Now, we can now go ahead and actually write out this equation in the Cartesian system. But to do that, we need to figure out how to convert the differential solid angle in the Cartesian basis as well. So that's just some algebra which you have to go through, which, you can pause the video and then check the algebra is right. So the elemental solid angle is just d omega is sine theta, d theta, d phi. And all of these angles are related to the L, M, and N Cartesian basis given by these three equations. So that's just a transformation between Cartesian and spherical coordinate systems. And to figure out what this elemental solid angle will be in terms of the elemental changes in L and M, you just have to solve for this Jacobian. Okay, that is again just basic calculus to do a change of variables in your integration. So I have done that here, and then you can pause the video and check these equations. But the upshot of this is d omega is given by this expression here. So d omega is related to dl dm divided by n, which is the z component, which is square root of 1 minus l square minus m square. So now we are done. So we basically get our the relationship we are looking for, where we have the visibility. Sorry, the notes have been cut out here for some reason. So this must be the visibility v of u comma v is now given by the integral over L and M. So that integral, double integral, basically comes from the integral over all solid angles of the sky intensity distribution given by this complex exponent, which basically just looks like a two-dimensional Fourier transform. So that is a two-dimensional Fourier transform relationship between the visibility and the sky intensity. So you can write the inverse Fourier transform where the sky intensity, modified of course by this geometric term, is given by the inverse Fourier transform of the visibility. And so in typical interferometry literature, you would refer to the sky plane as the LM plane and the visibility plane as the UV plane. And so this equation is basically telling you that if you build a telescope which measures these visibilities, so these 2-point correlation functions of the electric field on a 2D plane at different locations U and V, once you have all of that data stored in a computer, you can go after the fact and apply this inverse transform relationship to figure out what the sky intensity distribution is. So this is basically telling you that in radio interferometry, we don't directly measure the brightness of every pixel on the sky. What we instead do is we measure components of the Fourier transform of the sky intensity distribution. And after the fact, in post-processing in our computers, we take these 2-point correlations of visibilities, which are the components of the Fourier transform, and basically do an inverse Fourier transform to get back the sky intensity. And so that's the basic insight of you need to understand image formation in radio interferometry.